Interpretations of the derivative. So now that we've spent a bit of time talking about how we compute the derivative, it's really important that we understand the inner workings of what's happening on a small scale when we approximate. Additionally, we need to make sure we understand what the units of the derivative are when we're calculating such things. So far in this course, we've used what's called Newtonian notation. So that's because it came from Sir Isaac Newton. So that notation is what we've been using that looks like the f prime of x. When we use that prime mark, that came from Newton, and that's what we mostly use because the shorthand's a bit easier. However, while Newton was developing calculus, Leibniz was also developing calculus, and Leibniz used a slightly different notation. He used the notation dy dx. Now, dy dx represents the derivative of y with respect to x. So in that shorthand notation, y is our dependent variable and x is our independent variable. So what happened was Leibniz took the general formula, y equals f of x, and he said, okay, what if I take the derivative with respect to x of y? And hence we get dy dx to also represent that we're taking the derivative. Now, we can use these notations interchangeably. Generally, you will see Newtonian notation, but when we talk about things like units, sometimes it's really helpful to look at how Leibniz wrote out the derivative to understand where the units were coming from. This also matches up with what we know about average rates of change. So when we talked about average rates of change to get to the instantaneous rate of change, we were looking at the ratio of two things. We had something over something, and that also helps us understand where the units come from. So remember, when we talk about dy dx, we're talking about small differences in the y values over small differences in the x values to approximate the derivative. So ultimately, when we talk about the units of the derivative function, it's going to be the units of the dependent variable divided by the units of the independent variable. And that matches up with Leibniz notation. So dependent is our y over independent, which is our x, which is the same thing we got when we did average rates of change calculation to estimate, because we were doing the change in y over change in x, and we were able to match up those units. So let's go ahead and look at a couple problems and start to understand how these units work and how we can attribute them to different problems we're working on. Suppose that the position of a falling stone is given by s of t in meters and time t is given in seconds. Then s prime of 4 equals -7 means... So here, I want to remind you that in physics, position is often represented by the function s of t. It doesn't have to be. We could use f of x or g of t or any other representation, but the convention is to use s of t when you're talking about position. Now here, s of t is our dependent value here, our dependent variable, and that's given in meters. And time t is our independent variable, and that's given in seconds. So s of t is our dependent variable, and time is our independent variable. So when we talk about s prime of 4, the derivative at 4, the number that you plug into a function or the derivative, or really any number you plug in anywhere, is always an independent value. So it's going into the independent variable. So 4 is representative of our independent value. So our independent variable has a units of seconds. So this 4 is in seconds. Now this -7, that's our derivative when time equals 4. So that's the rate at which our position is changing when time equals 4 seconds. So to get the units of the derivative, again, we're going to take the units of the dependent variable over the units of the independent variable. So here, that means I'm going to have meters per second. So here, once we've attributed the right units to our numbers, we can construct a statement that represents what we're looking at. So here, after the stone has fallen for 4 seconds, it's moving at a rate of -7 meters per second. So we need to make sure our sentence has the numbers paired up with the right units, and then there's lots of ways we can write that. We could also say something to the effect of, the stone is falling at -7 meters per second after it had fallen for 4 seconds. So there's not one right way to write a sentence or to talk about what it means, but the idea is that the number is paired with the right units. Then there's lots of ways you can say the same thing. So in this particular example, if delta S represents the change in position during a time interval delta t, so delta usually means change, okay? So the change in S, or the change in position, during a small time interval, and we're looking at the change in time, and if the object continues to move at this velocity, we could also make a statement that the change in position is equal to -7 times the change in time, as long as the velocity is small and as long as it's not varying. So that means we can predict what the change in position is going to be by multiplying the change in time times -7, since that's the rate at which the object is falling. So in general, we can write the change in position is approximately the derivative at that certain time times the change in time for small values of t. So in general, our change in position is going to be approximately the derivative, or the rate of change at which something is falling or moving, times the change in time for small values of t. Now, what we're trying to understand is that for a small change in time, if we multiply it by the rate at which we're falling, it will help us understand the change in position, or how much it changes. We're going to use this idea later on to be able to predict what's happening at different points on a function. Now, if the derivative of a function is not changing rapidly near a point, so if it's not doing anything extreme, it's not jumping or looping or doing anything crazy, then the derivative is approximately equal to the change in the function when the independent variable is increased by 1 unit. So when we talk about what the derivative means, we're talking about what happens when we change the independent variable by 1 unit. What is the impact on the dependent variable? If we go back to our s prime of 4 equals -7, what that tells me is that if I go from 4 to 5 seconds, so 1 unit change in seconds in the independent variable, I'm expecting my position to change by -7 meters. So it will fall an additional 7 meters. So again, it's the idea of changing your independent variable by 1 unit. What sort of impact does that have on the dependent variable? That's how we interpret what the derivative is telling us. So let's go ahead and look at some examples and get used to attributing units and making meaning from our derivatives.